Start. Okay. This is physical vapor deposition, and today we shall discuss on this topic what we know as sputtering. Now, sputtering has a classical definition, and this is a process which is basically dislodgement and ejection of material from a solid or liquid surface in atomic or molecular scale due to momentum exchange with an incident energetic projectile. Now, this sputtering is actually a physical vapor deposition process which can be used for depositing various types of elemental metal. It can be a compound or it can be an alloy. So, deposition of sputtered material, how does it work? We can have a very close look. So, deposition of sputtered material, actually what happens? Sputtering is ejection of the material, dislodgement of the material from a surface which we call in the language of sputtering as the target. This is not actually the deposition process. In fact, the material or the surface which we need to coat or cover with a layer, that has to intercept this flux of material which will be ejected by this impingement of the energetic projectile, and this is called actually the deposition process, and sputtering is the ejection of the material and intercepting that by the substrate material which will condense over the surface of the substrate, that is actually known as sputtered deposition process. Now, here comes very interesting thing, that principle to practice of sputtering, that means how to put this principle or theory of sputtering into a practice and a process of practical interest. So, first and foremost thing one has to do is generation of this energetic particle. Now, this sputtering is conducted in a closed vessel or a chamber which is evacuated, and inside that chamber one has to generate energetic particle, and which will be the ions of heavy inert gas like argon. Now, to get this ionization, again one has to ignite one electric discharge, and in that electric discharge ionization of the argon, that will take place in the region adjacent to the surface of the substrate, and this ionized gas of argon, that is also known as plasma, and in the process obviously within that chamber one has to keep one cathode and anode to initiate that electric discharge, and in this whole process the target material, that means the source material from which the material will be dislodged, and it will emerge out like a flux, like a stream of sputtered material, that is actually kept as cathode. So, this target which will serve as cathode, that is actually negatively biased. Now, scheme of sputtering apparatus. Now, let us have a quick look. So, here schematically we can show like that. This is a chamber which has to be evacuated. So, it is connected with the vacuum system. And obviously, there will be one target which is actually the source material. So, this will be the target, and that will be isolated from this chamber wall, and it will be negatively polarized. So, this side polarized. So, this will be grounded, and at the same time the body of the chamber can be also grounded. So, what is going to happen in this process? Here we can keep the substrate, that means the material or the object which need to be coated. Now, here this substrate, this is actually the substrate material which can be grounded or which can be also biased. So, this can be in the ground state or it can be also polarized. So, what is going to happen? Say for example, this is titanium target, that means basically it is a titanium disc or a titanium plate having a cylindrical surface or a rectangular surface, and this is the negatively polarized target with this power supply. So, this is evacuated down to at least 1 into 10 to the power minus 4 to 10 to the power minus 6 torr. So, that is the order of at least one has to reach that, and then actually what we have to have one entry point for argon, which will be high purity argon, and this high purity argon will be admitted in a metered quantity into the chamber, so that its pressure can build up maybe from 1 millitorr to 10 millitorr, and in that case it is highly polarized, and in that case there will be one electric discharge because of the electron which are available on the surface of this target. This floating electron that will be attracted and that will hit this neutral argon in this zone, and here we have splitting of argon ion plus 1 electron, and this splitting will occur because of this electron will be flown in this direction because of this negative positive polarity on this side. So, there will be one cathode and one anode. Even this wall of this chamber can be anode, or we can also put one auxiliary anode, and during this course of movement in the space between this substrate and the target, what is going to happen? This electron will strike and have a collision, splitting this neutral argon to positive argon, and as a result this positive argon now will be accelerated towards this negatively biased surface, and that will strike on this surface and it will transfer the energy, and as a result the material will get dislodged from this surface, and at the same time it will also emerge, it will be ejected from this surface and it will flow in this direction like a flux of sputtered material. And if this substrate is placed in front of this target, in that case this substrate surface will intercept this stream of titanium vapor, and that will deposit over this surface on this, and it will condensed over. So, atom by atom titanium will build up and will grow, and it will finally appear as a coating of metal. So, this way one can look into the basic process of sputtering, and obviously what has to be done, that control of the pressure, this control of the pressure on one side, here of course we have a metering valve like a throttling valve to control the pressure inside the chamber, and then we have metered quantity of argon which will be flown through one MFC. So, that is the quantity which will be admitted. The pressure is controlled by this throttle valve on the downstream side. So, there should be one pressure sensor continuously monitoring the pressure, and we have to have some polarization of this target and a power supply. So, with all this one would expect that sputtering from this target surface, and it is the deposition on the substrate. So, this is actually called a DC planar diode, because it is working like a DC mode and it is like a diode, and it is the plane surface. So, it is called a DC planar diode mode, very simple form of sputtering apparatus, but even with this simple form of this apparatus, one can see how this process can work, and at the same time how this material can be deposited from this target, and there will be continuous gradual erosion of this material from the target, and this will be depositing over this surface. So, here one has to obviously operate the process parameter. That means, there must be some process variable which has to be handled with delicacy, and so that the desired outcome, we can have the desired outcome. Desired outcome means at least we are interested in the growth rate of this coating. This is point number 1. That means, how many micron of this coating is building up on this substrate surface. Number 2, uniformity of the coating over this entire surface of the substrate. This is also another issue, very important issue, considering various engineering application. And the number 3 is the structure of the coating, smoothness of the coating, density of the coating. Is there be any contamination, any poisoning of this coating? All these issues have to be also properly addressed, and then comes the density, obviously, then adhesion of the coating with the substrate. That means, how this interface is built up at the very initial stage. So, all these questions have to be properly addressed, and this is exactly the sputtering process. So, one has to look for this cathode current density. That means, when this voltage is applied, so once there is ionization, so we can also find, or we can determine straightforward the cathode current, that means ion that is collecting on this surface, and from this surface area we can find out the cathode current density or even the power density. Then also the discharge voltage, that means the voltage which will be also recorded on the power supply unit. So, both cathode current and the DC discharge both will be displayed, and then argon pressure which will be monitored here by this throttle valve on the downstream side, and then this SOD. SOD means the standoff between this target and one anode plate. So, actually this distance of the substrate, it is in between. So, substrate can be one anode, or substrate can be also grounded, and we can also have a separate anode. So, this distance, standoff distance between this surface or substrate surface or a separate anode, that is also one important parameter, because the pressure inside the chamber and the mean free path, that is one point one has to consider, and also the flight of this mass of sputtered material, which will follow this path and it will finally arrive here. So, whether there is collision or it is moving freely, all these issues are also taken into consideration. Now, in the sputtering process, one cannot just ignore this point, that is called sputtering yield. Sputtering yield is that the ions which are the projectile, in this case which are going to hit or strike the target surface. Now, one ion, say for example, one ion is going to strike this surface, and as a result of that how many atoms will be ejected. So, that is actually the capability of a single ion which can cause dislodgement followed by ejection and then this flow of the sputtered material like a stream. So, all these series of processes are actually at the result of this heat by this argon ion, which is serving the like a projectile. So, this is one thing. So, that is actually sputtering yield, number of target atoms which are being ejected per ion, per single ion. Then it depends upon the target species, that means it is the atomic mass of the target, and then also it is impinging species, that means it is also the atomic mass of the argon in this case, that is also one thing. Then also the incident energy, that means it is striking with a velocity. So, it is mass and velocity, basically it is a kinetic energy with which it is going to hit the target surface, resulting in ejection and dislodgement of the atom, and also the angle of incidence, at which angle it is going to strike. So, all these things taken together, they are actually going to finally determine what will be the number of atoms which are being dislodged and ejected per unit ion. Now, we go for sputtering yield and sputtering rate. So, sputtering yield, we understand that how many atoms are being ejected per strike of one ion, per unit strike. Now, here comes the sputtering rate. Sputtering rate means here, if we consider this as the substrate surface, how it is growing. That means, it will be say in nanometer scale or micrometer scale, how it is building up on this. So, a relation is already available, that means that sputtering rate is given by 62.3 and it is J into S into M T and this is divided by rho, so many angstrom per minute, that is a relation one can look at, and this is a very handy relationship. So, what are these Js? That is actually ion current density, and which is given ion current density milliampere per square centimeter of the target surface. What is S? That is actually atom per ion. That means, so many number of atoms of the target material per ion of argon. This is actually atomic mass of the target material, atomic mass, and this is density. So, with appropriate coefficient we arrive at this. So, this is an expression for the growth of coating which is continuously being built up on the substrate surface. So, this is one very important relation from which one can assess the growth rate. Sputtering yield and angle of incidence of the projectile. Now, this is also important in that sputtering yield, this sputtering yield, that sputtering from this relation we see, this is the sputtering yield. It has a determining, it is a determining factor determining this growth rate. Now, here this angle of incidence also it does come in picture in this, that this is actually the surface, and if we consider this is a normal, then it can have, this is the angle theta at which this incoming argon ion is going to hit or strike this target surface. Now, there is a distribution by which one can see that this is sputter yield and this is the theta, and it is something like that, it goes like that and then it almost have a drooping. So, this is almost 90 degree and here it is somewhere little below 90 degree, we get this value critical here where it is corresponding to theta max. Now, this angle of incidence normally usually we consider normal angle of incidence. So, it is actually argon ion which are going to strike under the action of this electric field normal to this surface, but here what happens, this surface what we are showing, that is a theoretical one, that means it is optically flat and horizontal, but in practice this is not the case. We have unevenness on this target surface. So, even if we have a normal incidence of the target on the target, this argon ion, depending upon the undulation on this surface, depending upon this undulation on this surface, if we consider this is striking at this point which is normal with respect to the axis of the target. However, with respect to this surface this is not actually straightforward. So, here one has to draw one tangent and normal. So, if we draw at this point one normal and one tangent, then we get this angle theta, and which is somewhere in between this 0 to 90 degree, and as a result we can see the angle of obliquity of this incidence, and which is not always 0 degree. Whatever may be the case, we see a distribution of sputtering yield with this angle of incidence. Now comes this momentum exchange. It is actually a well known principle or theory that it is a momentum exchange between this incoming argon ion and the atom of this target particle. Now, here if we show this surface and here we consider the spheres as one arrangement of atom. So, this is one arrangement of atom, and what we can see, say for example, one argon ion is hitting and it is intermediates, say it is actually hitting this surface and it is in between these two atom on the surface of the target. So, this is actually the target surface. So, it is actually said in the theory that because of this strike, what is going to happen, these two will be immediately affected, these two atoms are going to be affected immediately. That means, there are actually it is a knock on. So, it is called knock on process. So, one is called low energy knock on and the other one is called the primary knock on. So, as a result of this strike from this side, this atom is going to move in this direction and that we call low energy knock on, and during this process what is going to happen, as it try to move in this direction, it will try to displace this atom, and as a result it has a tendency to eject in this direction. So, this is going to be an ejection of atom because of this low energy knock on. Now comes the primary knock on mechanism. Primary knock on means this is going to be pushed inside this lattice. So, this is actually the primary knock on that will be pushed inside this lattice and it may come up to this point and then it will move in this direction just like a reflected atom. So, it will move in this direction up to this point and then it will be reflected. So, this will be the movement and then this will be the reflected movement, and during this reflected movement this atom which is actually representing this primary knock on, this is going to hit this atom from the back. So, it is from the rear, it is going to hit it, strike it, and as a result of that it is also has every chance to get released, liberated, and this is an ejection of the atom. So, these are the two well known principle of momentum exchange by which this low energy knock on and primary knock on take place. So, this is just a lateral movement and this is just sideway. So, it is a push from this side and this is because of the reflection. So, this one is released and this atom is also released. So, this way this ejection of the atoms from the surface of the target material that can take place. And here one can also understand that this energy which is transmitted to this target atom. So, energy which is transmitted to this target atom, this will be actually if we consider this is the transfer. So, this will be proportional to MT into MI divided by MT plus MI whole square, this fraction of the input energy, that means the energy with which this argon ion that strikes, it will be that part of the energy will be transferred to this target atom, and the energy with which this will be reflected from this surface, that will be given by mt minus mi by mt plus mi, that is whole square, into this input energy of the incoming species, that means this incident ion, into the energy of the incident ion, that part will be the reflected energy, it is rebounding. So, this is actually transferred with this incoming energy, and this part actually reflected, this is the coefficient along with this one. So, this is basically a momentum exchange process by which this ejection of this atom from the target surface that may take place. Now, all these things are done, actually this velocity, energy, whatever may be, that will be gained by this incoming ion as a result of the electric field, and that is actually done, created by polarizing this target, and which is serving like a cathode. So, here one graph is very important, not only from academic point of view, but also for designing of the sputtering apparatus or the sputtering device, and this diagram can be shown, illustrated in this form, and this is in this way. So, this side we show the voltage, that is the breakdown voltage. That means, inside the chamber we have the cathode and the anode, and a discharge is going to occur, and this discharge is initiated at that point of breakdown voltage, and that is the threshold value. But this is not just independent of anything, it has a relation, or it depends upon one parameter. It is not just a parameter, it is a combination of two. So, on this y axis we show breakdown voltage, and on this we show it is actually P into D, and that is called P into D torr centimeter. So, on this side breakdown voltage, that is in volts, and this side we have torr centimeter, and with that what we can find here, this curve look like this. So, one can find out, immediately recognize a point which gives the minimum value of this breakdown voltage. This is V minimum, and that is corresponding to a particular value of P into D, and on both the sides, to excite this discharge, to initiate this discharge, one will require a higher value of breakdown voltage. Now, this is one thing we can look here. If we work with low pressure, this is the low pressure side, or a shorter SOD, so shorter target anode, that means inter electrode space. So, this inter electrode space, if it is short, if the pressure is low, then P and D both will be low. So, as a result, what we find, that the threshold voltage to cause breakdown of this cause this discharge, initiation of the discharge of this plasma, that also require a high voltage. While on the other side, other end, we also see there is a requirement of high voltage, the requirement is rising steadily, and this side what we find, if we work with a high pressure, or if the distance SOD standoff between the two electrodes, if it is too high, then also the required voltage, the demand will be quite high. So, this is one very important information and a data which will be required by the designer of the sputtering machine, and depending upon the working range of this machine, one can design its operational range. That means, at what pressure it can work, what will be the standoff distance or size of the vessel, and at the same time what will be the available voltage as per the power supply, so that the machine can become an useful source of deposition process. So, this way one has to look for this minimum voltage for a given P into D, that value. Now, this is voltage current characteristics of a DC discharge. So, this voltage current characteristics of a DC discharge, it is very relevant to sputtering. So, one can consider this one. So, here what we find, so this is actually the voltage and this is the current VI characteristics. It goes like this, and this is the peak point, and then it drops down, then it becomes steady over a wide range, and then again it rises, and finally it has a fall, and then it is also rising. So, let us identify various sections of this graph. Now, this part is called, from this part, that is called ohmic conduction. This side, that is called Townsend discharge. This is this drop, fall of voltage without any change in current. This is actually called breakdown, process of breakdown. After this, what is interesting, that without any change in further rise of voltage, the current keep on increasing, and this we can see here. This is a typical characteristics of a DC discharge in a vacuum tube. So, this goes, and this is called actually normal glow. It is actually discharge with glow, and this part, from this point what we see, that if we like to increase current, that will cause an increase in voltage. So, this is called abnormal glow, and it is exactly where we carry out or conduct sputtering. So, this is the zone where sputtering is conducted, and after that, if one try to increase current, then there is sudden fall of voltage, and what we see, it is almost going to be an arcing. So, we can see various stages, variation of voltage with current, and in that process, when we find the abnormal glow, that is the zone where this sputtering process occurs, and that is conducted. Now, this is actually current voltage characteristics for planar diode sputtering. Now, what we have seen, the voltage, breakdown voltage versus P into D. This P into D means process pressure and the target anode distance, that means SOD. Next, what we are looking at, that is the zone where we have abnormal glow, that means here along with the current voltage is rising. This is the zone where sputtering takes place, and now comes in the sputtering what we see, that this is actually VI characteristics. Now, here one has to, particularly the designer of the sputtering device and the operation, for that this VI characteristics is so important. Now, say we can draw one curve like that, and this curve, it is true for a sputtering device having a fixed dimension, that means fixed SOD, and only what we can change, say it is just for one target material, one projectile material which is going to strike the target, all these things are fixed. So, what we are changing here, it is only voltage and current. Now, what is our output? It is actually current is what we like to have, because larger the current, that means more will be the ionization and more will be the ion current, and that will have a immediate impact or effect on the deposition rate. So, one can immediately look into this fact and take necessary step how to change the slope of this curve. Now, this is say for a particular pressure. So, this is actually process pressure. So, with this process pressure we can have a VI characteristics. However, if we change this process pressure, this characteristics may change. Now, this change means for all practical purpose, from design and operation point of view, from engineering point of view, one should look at the current and the voltage. That means, with what voltage we can achieve that cathode current. Obviously, lower the voltage benefit, more will be the benefit. So, the point to be considered here is with what ease we can have this large magnitude of ion current, and this is one of the subject in the design of the cathode. Now, it is a planar DC diode, very simple. So, here what we find, that this curve is very, its rise is quite steep. That means physically it means for a small value of current we have to go with a very large value of these volts. It can be few thousands of volt, few kilovolt, and we cannot even get a high value of current. Now, for all sputtering operation one may expect to have certain cathode current, means certain cathode current density, power density with certain pressure and a reasonably applied voltage which is not too high. So, for this a special consideration has to be made in the design of the cathode. That means, with the small value of voltage with a pressure range which is very favorable to get one of the very best structure of the sputtered coating, one can get a high value of cathode current. So, this is one of the requirement in the design of the sputtering system. Now comes planar diode sputtering. One can look into this planar diode sputtering. That means, here actually if we have one target or cathode, which is cathode, and on this side we have the anode, and the whole thing is within a chamber. So, this is polarized, you have argon entry, all are all polarized, obviously these are all polarized. If this is a situation, then what we can find out here, we have three distinct zones. This is the main plasma volume, this area which is shown by this this area, and this space, this is called actually cathode dark space. And this zone anode sheath. So, what happens? The electrons which are available very close to the target surface, these are known as primary electron. That means, electrons which are available here, these are called primary electron, and these have to be brought in within this main plasma volume, and for that we have one accelerating voltage, and during this process these are known as, that means the electrons which are in close vicinity, close neighbor of this target or the cathode, this is target or cathode. So, these are called secondary electron. So, these are actually secondary electron. Now, when they are brought in by this accelerating force inside, they are called here this E, that becomes the primary electron. Now, they have gained certain energy, here they are very weak. So, now they are within this field, they are the primary electron. Now, this primary electron, they are going to strike, make collision with the argon neutral, and here it is very important that this strike or collision must result in argon ion, one argon ion plus one electron, and with that this argon ion is going to, now it will be accelerated on this surface, and with that it is going to strike this surface, causing, that means what has been already mentioned, that means this ejection and dislodgement of the target, but at the same time this argon ion can also cause emission of what we call secondary electron. So, one argon ion that is going to eject the atom from the target, but at the same time to generate secondary electron, and which once it enters this plasma volume, that becomes the primary electron, and this way the process repeats itself. So, it is very important that this primary electron must generate argon ion, and this argon ion will be accelerated towards this target surface. So, this is just a cyclic process, and this way the process will keep on going, and in this what is important, that partial pressure of argon, this target voltage, this breakdown voltage, and this cathode anode this distance, those are put together, they have a combined effect, and accordingly we can see as the output what is the cathode current and also the deposition rate. So, this is what we know as very simple planar diode sputtering. Now, in planar diode sputtering we can have lot of variations. So, though it is simple, it can have lot of variation, that means it can be a single target machine, at just mean that means one cathode, it can be an elemental cathode, say any metal, it can be titanium, aluminium, copper and so on, it can be one alloy, it can be even compound, it can be a alloy of say silver, copper, it can be nickel chromium alloy, it can be titanium aluminium alloy, it can be a compound, say for example aluminium oxide, molybdenum disulfide, tungsten disulfide, something like that. But instead of single target, we can also have a multi-target machine. Multi-target machine means we have this kind of vacuum chamber, and the target may be positioned like this, and here we have the substrate. So, the deposition, this is intercepted. So, there are two materials and which can have simultaneous deposition, instead of 2 we can also have 4 targets. So, here it is an intermixing, that is also possible, but by this multi targeting what we can have? By this multi targeting we can have either, instead of a monophase we can have a multiphase layer. That means both are ejecting material. So, both will form an alloy. So, it is not a monophase, it becomes a multiphase layer, but it can be monophase multilayer, it can be just. So, it is a multi-phase single layer, but it can be a monophase multilayer, that means it can be interrupted. So, say this is target A and this is target B. So, it can be just like an alternate layer A, and after that we can put another layer of B, and this way the process will repeat. Of course, in this case we need a precisely controlled automation to run the system, to have a perfect blending of this multi-layer, having the required thickness, uniformity of the thickness, then structure of this each layer. So, those issues should be there, but the advantage is that by this alternating, by just sandwiching, the mechanical property, for example, can be remarkably improved by this way, but it can be also a graded layer. Graded layer means we can start up this way, say this is just the substrate, and with this substrate what we can have, it is A here 100% A, but then what we can do, we can have a grading over this may be a thick layer. So, this is A, and here what we have, this is actually A and B together, say this is A x B y. In that combination we can have a buffering. With this buffering, the value of x and y can keep on changing continuously. So, from A to we get A x B y, and as we go in this direction, that means as the coating keep on building and thickness keep on increasing, what we have finally at this end we can have just pure B. So, we start with 100% A in this position, and then it is gradually converted into A x B y. Value of x is at the very beginning very high, y is low, but as the coating thickness keeps on increasing, value of x will be decreasing and y will be increasing, and finally it will become 100% B. So, this A is compatible to the substrate. However, B has the required property, functional property. So, B to substrate, that can be handled by this sputtering, and in this case obviously we can change, we must know the sputtering rate of this cathode A and the sputtering rate of this cathode, that means target, and that one has to look from this curve, and this is actually what we know, that this sputtering yield, which if we say this is S, and here we have the this energy which is given in electron volt EV, that is the energy, and with that we can have available energy, we can have a sputtering rate like this. For a material we can have a sputtering rate like this. Say for example, we can give this illustration, say it starts with say 0.5. So, 0.5 means S is, what is S? S is actually target atom liberated by the strike of one single argon ion. So, it is so many atoms of the target material for one single strike of one argon ion. So, this can be as high as say 3.5 to 4, and here it is as low as 0.5. So, it depends upon material. So, it can be on this side high end, it can be silver, and on this side it can be titanium, but this graph should be available, and one can find out from this graph, and doing some experiment and trial run he can find out what should be the actually the sputtering rate, and accordingly one can find out what should be the cathode current for A and what should be the cathode current of B, and gradually that has to be adjusted to see that it is an absolutely a graded layer which can give you that super quality of the composite coating. So, this is multi-target. Now comes substrate biasing. Now, this is also one important issue, that what we have so far considered, it is just the target, and here we have the substrate. So, target will be negatively biased, and this is grounded, and this is actually the chamber. 2 minutes. Okay. Oh, so it should be the substrate, and here one can look into this substrate, and so here we can have some kind of biasing, and with this also we know that With this we can have substrate biasing, that means it can be during sputtering, it can be before sputtering, and that can be used for cleaning the substrate and also changing the structure of the substrate during sputtering. So, it is just not that argon is going to strike this surface for getting this ejection of the material, but it can be also very closely precisely controlled impingement on this surface to have proper structuring of this built up layer. Similarly, what we can have? We can also have admittance of the reactive gas in addition to argon. So, when we have target material falling on this, we can also see that if we have one reactive gas, then this reactive gas and this material which is getting condensed over that surface, they can also form a coating of a product which is the reaction, say titanium from this target and nitrogen. So, we can have also TIN. So, this is called reactive sputtering. So, with this what we can see that in summary, sputtering is basically ejection of material from a solid surface because of impingement of the same by highly energetic projectile. The argon ion strikes the source or the target surface which is acting as the cathode in the sputtering chamber. The flux of the sputtered material is intercepted by the receptor surface of the substrate. The cathode current, discharge voltage, process pressure and the stand-off distance are the main process variables. A monophase or multiphase coating can be deposited by sputtering. It can also be extended to deposit multilayer or graded layer coating. Substrate bias and substrate temperature may have strong influence on coating properties.